On February 19, 2026, a paper was published in Geophysical Research Letters that changed how we understand one of the most bizarre planets in the solar system. Scientists using the James Webb Space Telescope had just produced the first-ever three-dimensional map of Uranus's upper atmosphere, and what they found inside it, glowing giant, completely invisible to the human eye, has been there the whole time. We just couldn't see it. Uranus has auroras, massive ones, and they work in a way that has no equivalent anywhere else in the solar system. For the first time, an international team of astronomers mapped the vertical structure of Uranus's upper atmosphere, uncovering how temperature and charged particles vary with height across the planet. The observations were made using Webb's near-infrared spectrograph instrument, which watched Uranus for 15.4 hours on January 19, 2025, close to a full rotation of the planet, which takes about 17.2 hours. The result is the most detailed portrait of Uranus's atmospheric structure ever produced. And at the center of that portrait are auroras unlike anything we've seen at any other planet. To understand why these auroras are so strange, you need to understand what an aurora actually is, and then understand why everything about Uranus breaks the rules. On Earth, auroras form when charged particles from the solar wind travel along our planet's magnetic field lines and collide with molecules in the upper atmosphere. The collision excites those molecules, and they release energy as light, the greens, reds, and purples of the northern and southern lights. Earth's magnetic field is roughly aligned with its rotational axis, so the auroras appear predictably near the poles. They're beautiful, but they're geometrically straightforward. The magnetic poles are where you'd expect them to be, and the auroras form there. Uranus does none of this cleanly. Uranus has the strangest magnetosphere in the solar system. Its magnetic field is tilted about 59 degrees from the rotational axis and offset from the planet center by roughly a third of the planet's radius. This means the magnetic field doesn't emerge from the core symmetrically the way Earth's does. It wobbles. It tumbles. As Uranus rotates, its magnetic poles don't stay in one place relative to the Sun and the solar wind. They sweep through dramatically different orientations every single Uranian day. On Earth, we have a name for what happens when magnetic poles shift relative to the planet's rotational axis. We call it a geomagnetic reversal. It's a catastrophic event that happens once every few 100,000 years and that scientists study with deep concern for its effects on satellites, communications, and navigation systems. At Uranus, the equivalent of a geomagnetic reversal happens on a daily cycle. Every single rotation, the magnetic geometry reorients itself, the solar wind hits it from a completely different angle, and the entire magnetosphere responds. The auroras that result from this geometry are not confined to the poles the way Earth's are. Because the magnetic pole is tilted so far from the geographic pole, the auroras don't sit neatly at the top and bottom of the planet. They sweep and roll across the upper atmosphere in shifting dynamic patterns that track the churning magnetosphere beneath them. They extend across latitudes that would be completely aurora-free on any normal planet. And none of this is visible to the naked eye, or to any conventional optical telescope. The auroras on Uranus glow in infrared wavelengths, light with longer wavelengths than human eyes can detect. The specific signature scientists look for is emitted by a molecule called H3+, a molecular ion made of 3 hydrogen atoms bonded together, with 1 electron removed. This ion is one of the most useful remote diagnostic tools in planetary science. Where auroral activity is intense, charged particles from the magnetosphere pour into the upper atmosphere and drive increased ionization. More H3+ forms, and it glows more brightly in infrared. Track the H3+ glow, and you're tracking the aurora in real time. This is exactly what Webb's near-infrared spectrograph did. And the three-dimensional picture it built is remarkable. Temperatures in the upper atmosphere peaked between 3,000 and 4,000 kilometers above the planet. Ion densities hit their maximum closer to 1,000 kilometers above the cloud tops. Those numbers describe a layered, structured atmosphere. Not a uniform shell of gas, but a complex vertical environment where different physical processes dominate at different altitudes. The temperature peaks high up, driven by energy pouring in from the magnetosphere. The ion density peaks lower, where the atmosphere is dense enough to accumulate charge before it dissipates. The study also found 2 bright bands of auroral emission close to Uranus's magnetic poles, and between them, something unexpected. A region where both emission and ion density drop sharply. A quiet zone. A gap in the auroras where you'd expect activity but find almost nothing. Scientists believe this depleted region is directly linked to the unusual geometry of the tilted and offset magnetic field. Essentially a shadow zone created by the magnetic architecture of the planet, where field lines converge in a way that cuts off the particle flow driving the aurora. Strikingly, This two-band structure with a quiet zone in between mirrors features seen at Jupiter. It appears to be a universal signature of strong offset magnetic fields, a pattern that emerges regardless of which planet you're looking at, as long as the magnetic geometry is sufficiently complex. There is another finding buried in this data that has nothing to do with auroras, but is quietly alarming in its own right. Webb confirmed that Uranus's upper atmosphere is still cooling, and has been cooling continuously since scientists first noticed the trend in the early 1990s. The latest measurements show the atmosphere is roughly 426 kelvins cooler than readings taken by Voyager 2 in 1986 and by ground-based telescopes in the decades since. That is not a subtle calibration difference. That is a massive, sustained, decades-long cooling trend with no clear explanation. It connects directly back to the central mystery of Uranus, the planet that emits almost no internal heat, that appears thermally locked in ways that violate every expectation we have for a world this size. The atmosphere cooling from above while the interior stays silent below paints a picture of a planet in a kind of long-term atmospheric transformation that has no parallel anywhere in the solar system. Now here is what makes this detection historically significant beyond just the science of Uranus itself. The majority of exoplanets discovered so far fall into what astronomers call the sub-Neptune category, worlds physically similar in size to Uranus and Neptune, which likely means similar magnetic and atmospheric characteristics as well. When scientists map how a wildly tilted, offset magnetic field shapes the ionosphere of an ice giant, they are not just studying one unusual planet. They are building a framework for understanding the most common type of planet in the galaxy. Every ice giant exoplanet we discover around another star has a magnetic field we cannot directly measure. But if we understand how magnetic field geometry drives auroral patterns in an ice giant ionosphere, we can potentially read the magnetic environment of distant exoplanets from their atmospheric signatures alone. A planet with a stable, pole-aligned magnetic field like Earth's is far better shielded from stellar radiation than one with a tumbling, chaotic field like Uranus's. Understanding where an exoplanet falls on that spectrum, and how to detect it from light years away, is one of the most important open problems in the search for habitable worlds. 30 years of trying. 30 years of infrared observations coming up empty, of astronomers pointing telescopes at Uranus and failing to pull the auroral signal out of the noise. Near-infrared observations had been attempted repeatedly since the early 1990s with no success. Then Webb stared at the planet for 15 hours with the most sensitive infrared instrument ever placed in space, and not only detected the auroras, but mapped them vertically, in 3 dimensions, across an entire Uranian day. The planet that everyone dismissed as the boring one keeps refusing to be boring. Its auroras are invisible, enormous, and shaped by a magnetic field that behaves like nothing else in the solar system. Its atmosphere has been cooling for 30 years without explanation. Its internal heat is missing. Its moons may hide liquid oceans. Its clouds smell like rotten eggs. Its largest close moon has a cliff 20 kilometers tall. And we have visited it exactly once. 40 years ago. For 6 hours. The James Webb Space Telescope is giving us something extraordinary. A second look at a world we barely glanced at the first time. And every time we look, Uranus turns out to be stranger, richer, and more scientifically important than we expected.